So in this video, I will discuss about neural networks and whatever the concept that I learned till now. I will explain this and will implement a small neural network library known as Micrograd, which is created by Andre Karpathy. We might know him very well. He was very influential person in the field of deep learning. So let's start with some conceptual understanding about neural networks. Okay. So most fundamental building blocks of neural networks are neurons. Okay, so what they do, they receives data and perform some operations on that and produce output. Okay, for example, we will use circles to denote neurons over here. For example, if I have two data points x1 and x2, we multiply them with some weights over here, w1 and w2. Okay, after multiply them with some weights, we initially set the values randomly of weights. Okay, with some random generator. Okay, so after that we do a summation on these values. Okay, after summation, let's say this will look somewhat like this: w1 x1 plus w2 x2. So whatever output we will get after summation of this expression, we will pass on this output to an activation function such as 10h or maybe ReLU. Okay, so what is the task of activation functions over here in the neural networks? So what they do is they introduce non-linearity into neural networks. Okay, so suppose what they do, if I don't add or don't pass the output of this expression through activation functions, so if you see, these expressions are linear in nature. So if we pass on this directly to other neurons or other layers of the neural network, then the entire neural network will become linear, and they will become good at solving linear problems. But when it comes to solve non-linear problems, they won't be able to solve with better accuracy because they don't have the ability to capture non-linear behavior of data sets. Okay, so what 10H do, basically, if you see the graph of the 10H, they transform whatever output they get between -1 to 1. Okay, and this is -1, this is 1, and this is -1. Okay, so suppose if I get the output of this expression as, let's say, -5. Okay, so I'll draw it over here. Let's say this is -5. So output of the 10H will be -1. Okay, in case of ReLU, what they do, if you see the graph of the ReLU function, this is somewhat looked as this. Okay, so if we get the output as positive values, then it will be the output will be positive values as it is. But if we get the expressions, or like suppose if I pass -5 into ReLU function, then my output will be 0 over here. Okay, so this is what happens in a basic neuron, and we use these neurons to build our neural networks. Okay, so we form different layers into neural networks using neurons. First layer is we called as input layer, through which we receives the raw data such as images or some values or some text that are converted into vectors. Basically, any numerical values, we will receive this from input layers. Okay, then these input layers are connected with some other bunch of neurons. These layers are called as hidden layers. So basically all the neurons from input layers are connected with all the neurons of hidden layers. Okay, so what they do, hidden layers, their basic operations over here is to process the input that they receive from input layer and extract the relevant features that they get out of it. Okay, basic advantage of the neural networks is that we don't have to explicitly extract the features out of it. They do it on its own. But in case of traditional machine learning algorithms, we have to manually like extract the features f1 f2 from the dataset, and then we can pass the features to model to make predictions. So in this case, we don't have to do it on our own. It figures out it on its own. It has the ability because of this structure. This has been inspired from the structure of a human brain, how the information flows from neuron to neuron. The same concept used over here in order to make some predictions. Okay, the final layer that we use for the neural network is output layer. So this is where we will get the output or the outcome that we like processed from the hidden layers. Overall, the output we get from here. Let's say we are solving any binary classification problem, then we might get output such as yes or no. Or in case of like if you are passing an image such as like a dog, okay, and we might get the labels of the data such as dog or cat. This is the basic functionality. Okay, you might know that we introduced weights over here. Check. Okay, so the nodes are the connections between the nodes have some weights. They explains the strength of the connectivity between the two nodes. Okay, so basically the main objective of the neural network training is to adjust the weights in such a way that the prediction that happens in the networks that improves at every iterations. Okay, every iteration we adjust some weights, values of the weights, tune the weights such that it understand the pattern and make most closer predictions with an actual value. Okay, so this is what we understood. These are called as, let me explain you again. This is input layer, this is hidden layer, and this is output layer. Okay, so I have talked about weight adjustment, so how they are done. So to understand this, we have to understand the concepts of derivatives. Okay, derivatives and partial derivatives. So to explain this, let me take an example over here. Let's say, for example, if we have a function, let's say 3x square plus 4. Okay, so what derivatives tells us that it measures if I change the value variable of a function with some amount. Let's say if I have a function, let's say I have a value of x as 3. If I change some add some tiny bit amount into this value, then how this change in the value of x gonna affect the output of the function. Okay, the measurement of this change is known as derivatives. Okay, so let's have an example over here. Let's solve this and let's understand how this works. So the basic formula of derivative is f of x plus h minus f of x upon h. So for example, for in this case, let's h will be 0.01. Okay, let's do calculations over here. Let's calculate the value of f of x plus h. 3 into 3.01 square plus 4. Okay, if you do the calculation, then you will get around 31.18. Okay, what is the value of f of x over here? F of x will be 3 of 3 square plus 4, so this will come up as 31. Okay, so if we apply this formula over here, what we will get? This will be 31 minus 31.18 minus 31 upon 0.01. Okay, so after solving this, we will get 18 as an answer. So this 18 will tell us that how, in which rate the function's value will affect after changing the value of input variables or the variables that are inside the functions. Okay, so we use the same concept over here, and in real world we deals with a lot of multivariable functions. Suppose we have functions like 4x square minus 3y plus 6z. Okay, so here we have multiple variables in a function. These are also known as multivariate functions. So here in this case, what we do, we calculate partial derivatives. Okay, what we know is as partial derivatives. Okay, so in this case, what we do, we calculate the derivative, but we calculate the derivative with respect to each and every variables of a functions. Like for in case of x, we will do df by dx. In case of y, we will do df by dy, and in case of z, we will do df by dz. Okay. One important point to note over here is this has some interesting properties that we use often in the neural networks. Okay, so these values has the ability to tell us the direction at which if we move the function, we will get the maximum value of that function. Okay, so this will point out the direction of the function, tell us the direction at which, like if we move in this direction, then we will get maximum value of that for particular function. Okay, this has the ability of partial derivative values. These are also known as by the way, gradients. Okay, these are known as gradients. So what we do, we already know the function's maximum value direction. So in order to minimize this function, what we'll do, we will move the function in opposite direction. Let's say if the direction of maximization is this, then we will move in opposite direction to achieve minimum value of the function. Okay, so how we use this concept in neural network training process? So for that, let's see the output layer. Okay, let's say this is an output layer and we got some value like 5 as an predicted value. Okay, and the actual value is 6. Okay, so what we do, we compare these two values and find out the distance between them. Let's say this the distance, and the difference what we say is 1. Okay, so this value will become our loss. Okay, that this is the overall loss of the network that it has made. Okay, so what we do after this, we will treat this loss as an function of minimization problem, and we will apply the concepts or the principle of partial derivatives over here. So we will treat this as a function, okay, that we try to minimize. Okay, so what we do, we will calculate the gradient of this function, loss function, with respect to each and every weights or the parameters that are present in a particular neural networks. Okay, so loss with respect to let's say weights and in the hidden layers or maybe in neurons. Okay, so we use these gradients. Suppose this gradient value we got, let's say we got the loss function as -4. Okay, so what we do, we will add whatever gradient value we got in order to decrease the loss. So we have to make the loss closer to 0. Okay, so what we will do, we will add the gradient, some amount of gradient, let's say 0.01% of gradient, because if we directly multiply gradient, then it won't be able to get the minimum at minimum. Okay, so if suppose this is a function, okay, and we try to find out the minimum of the value, if we directly multiply weights or add the gradients of the weight, then it will jump over here and here. It will not be able to converge to this minimum value. Okay, so this is how we update the weights and reduce the loss of the network. Okay, and this every iteration the loss get minimized, and this way the prediction become more closer and closer to the actual value. Okay, so this is how we train the models or train the neural networks usually. So these are the concepts that we need in order to implement the micrograd from scratch. And let's start with the practical implementation. Okay, so let's start the implementation part. So first we will create a class, okay, value, and we will define a init function with variables, data. I will explain whatever the variables that I used further in the video. Okay, children, let's say it is a empty tuple, operator with empty string, and label with empty string. Okay, let's instantiate all these variables. Okay, self dot data equals data, self dot op equals op, self dot labels equals labels, self dot we will create a new variable named as dot prev. Okay, we will set it as set of children's. Okay, now we will create a wrapper function in order to get the output out of it. Okay, so this will look like this. Okay, so we'll pass on self and return f string data equals self dot data. Okay, so let's create an object and let's test it out. Value 2.0 and b value 3.0. Okay, if I print out a, then I can see 2.0. Okay, if I try to do any kind of operations like plus on multiplication, then you see, let's do it, and if you see the result, yeah, it will give an error. It will say unsupported operand type, as these are all objects. Okay, so the default settings of additions and multiplication are not able to handle the type value. Okay, so we have to create our own custom addition and multiplication functions to perform these operations. Okay, so let's do this. Def let's do with add. This will take two arguments, self and other. Okay, and let's create a new variable to save the value. Okay, so we will create value and self dot data equals to self dot data plus other dot data. Okay, and self dot self comma other, and this is right. Okay, plus. So let me explain you what all these variables are and what is the role of these variables. Okay, so the children variable, what will do it, let's say for example, if I do operations like a plus b equals c. Okay, so in order to track what all operation took place before we get this output, we will save or we will pair these values as a children of c. Okay, so like c, we will set a and b as childrens of c. So this way we will use it to during the back propagation, as well as to visualize the process or the operations that are happening. Okay, so we use childrens. We use operators to just trace what all things are running, and this will be mainly used during visualization. Okay, label also will be used during the visualization process. Okay, prev we will use during the back propagation in order to find out which variable has which childrens. Okay, so that's it. Okay, now let's create a small function in order to understand how the computations happen during the neural network training process. Okay, so let's do one thing. Let's create a new variable c, and let's name this as c. Let's apply the labels as well over here. Label is equals to a, and for here label is equals to okay b. Okay, similarly for c, c dot label equals c. Okay, let's create another variable named as e. Let's put this value as 10 with label as e. Okay, let's create another final variable which will be equals to c into I am creating this variable just in order to show how it will behave in case of addition and multiplication. Okay, let's execute this, and this is not showing us. Okay, oh yeah, I just forgot to add the multiplication as well, so let's add multiplication as well. Okay, self and other. Okay, and we will do the same versus value self. Yeah, here we have to also return the output out, and here self dot data multiplied with other dot data, and we will save the children's self and other, and the operator that we used, multiplication. Okay, right, and return the final output. Okay, so I think it should be working right now. Let's execute this. Yeah, so now it's working. Now I'm gonna use a little code snippet to visualize whatever things happened inside this function. Okay, so we used a open source Graphis tool in order to create a interactive visualization graphs of the calculations that happen. Okay, so let me do this. Okay, so we are all set now, and I've created copied the small code snippet to visualize the operations. Okay, so we use here Graphis software. Okay, so let's see how it works. Draw dot of f. Okay, yeah, this way. So you can see how things are working. Like I added a plus b and got c, and we multiplied c with e and got f. Okay, I forgot to add the. Okay, let's just fix this, and let's add the label as well. F let's equals to f. Okay, let's run entire kernel, and now let's see. Okay, so now it's looking better. Okay, so far we have understood how to visualize the operations that we are doing now. Let's see how gradients are calculated over here. So for that we will create a new variable over here known as self.grad. Okay, and set self.grad for all the values as 0. Okay, so let's see how this will look. Okay, cool. Yeah, so initially we will set all the gradients of all the variables as 0. Okay, so before we start, we need to understand about how the gradients are calculated. Okay, so suppose if I want to calculate derivative of f with respect to f, so what it will be? It will be 1. Let's see the proof. Okay, so we know the formula of derivatives. It will be f of x plus h minus f of x upon h. Okay, so suppose if I add some amount of h into f, okay, so it will be f plus h, okay, minus f upon h. So this will cancel out and we will get 1. Okay, so we need to understand that derivative of a function with respect to itself will be always equals to 1. Okay, so let's calculate how we can find out df by dc. See, we know f is equals to c into e. So what will be the derivative of df by dc? This will be c. Okay, how? Let's see. It will be let's say this will become f. Let's say I add some amount of h into it, and we multiply with e minus c into e. Okay, upon h. This will become ce plus he minus ce upon h. Okay, so if you solve this, this will cancel out and this will become e. Okay, and similarly df by de will become c. Okay, so if we manually set the gradients, then let's look out how this will look. Okay, f dot grad will be 1, as we all know from the calculation, and c dot grad will be, c dot grad is df by dc. So that will be e, and the value of e is 10. So we will set manually as 10, and e dot grad will become as 5. Okay, correct. Now let's rerun this cell and let's see. Yeah, so we have updated the gradients of f, c, and e. Okay, so now how we will find df by dA? Okay, we understood how to calculate this was easy to find out df by dc, but as there is no direct relation between f and a, we have to use something else. So here what we do, we to find out df by dA, we use the concept of chain rules from calculus. Chain rules. So what it tells, so we know that a impacts c, c impact f. Okay, so we know that this is an intermediate value, so the new formula will become df by dA will be df by dc into dc by dA. Okay, so we don't know till now what is dc by dA. Let's calculate it. So dc by dA will be, we know c is equals to a plus b, right? So the derivative of dc by dA will be 1. Okay, how? Let's see. So if I add some amount of h into a, so then it will become a plus h plus b minus a plus b, sorry, upon h. So if you do calculation, then you will get 1 as an answer. Okay, similarly dc by db will also be 1. Okay, so what will be the value of df by dA? It will be dc, or df by dc, we know it's equals to 10. We multiply with the derivative of dv by dc by dA, which is equals to 1, and we get 10 as an output. Similarly the value of df by db will be also equals to 10. Okay, so let's change the value of gradients manually. Okay, so the new values of a dot grad will be 10 and b dot grad will be 10, right? Let's do it and let's refresh this. Okay, so now all the gradients are updated. Okay, so now you have understood. Let's do one thing. We have to manually find out the gradients and manually set those into variables. So what we do, we will create a function for that will automatically find out on which variable to calculate the gradient. Okay, so we found out how to use this logic over here. Okay, so we will use the same principle to implement in a code. Okay, so let's start with addition. So before that, we have to create a function, special function known as self.gradient. Okay, and we will set this as none. We will set that this function will do nothing. Okay, we will change according to the operations that we applied on that particular variable. We will change the behavior of this function. That's why initially we will set that function as none. Okay, we will initialize the gradient to an output by setting gradient as equals to gradient, and we will define the or logic for gradient function. Okay, let's say def gradient. Okay, so how this will do, this will update self.grad in case of we know that c is equals to a plus b, and then we found out that dc by dA is equals to 1. So what we'll do, multiply 1 into out dot grad. So this is a chain rule, if you remember. So what we have done here, in case of like if I'm finding df by dA, okay, so this is df by dA. What I have done is I just multiplied dc by dA into df by dc. Okay, this is what we do. Similarly, we will implement the same logic for multiplication as well. So what we'll do here, we will do the same out dot gradient equals to gradient. Okay, and we will change the logic of the function gradient, and here we have to also implement for others as well. Others.grad equals 1 into output.grad. Okay. Now we will do the same with multiplication. So what will be the output? Self.grad will be, if you remember, we were calculating df by dc. So in that case, what we found E, and in case of df by de, we found out C. So if we have self, then the output will be others.data, and if we have other, then we get self as a output. Okay, so we will implement this as a logic over here. So what we'll do, we will multiply other.data into out.grad. Okay, similarly for others.grad will be self.data into out.grad. Okay, great. So far we have understood how this does. Let's try out this thing, and let's run this cell again, and let's initialize all this again. And before doing this, let me do as a base case let's set f.grad as 1. Okay, and we will apply f.gradient over here. Okay, let's see. If I just do this, and let's see, yeah, now we got the output. Okay, so after implementing c.grad, let's apply gradient on it, and let's check what is the output. Okay, so if I refresh this, I will get updated gradients. Okay, so now we have seen this implemented the function that will calculate the gradients of this function. Let's do one thing. Let's automate the entire process. Okay, what we'll do for this, we will use the concept of topological sorting. So according to topological sorting, if we have a directed acyclic graphs, then applying this algorithm, we can sort these directed acyclic graphs. Okay, so before I explain you, let's implement it on a code. Okay, through that you will be able to understand it better. Let's create a function known as backward. Okay, this will take a self as an argument. Okay, we will create a empty list known as topo empty set named as visited. Okay, we will create another function inside the backward function known as build graph. This will build a graph. Okay, build graph. Okay, and it will take an argument as v. First we will apply a if statement. We will check if v is not in visited. If it is not, then we will add it inside the visited set, visited.add. Okay, and v. Okay, now we will check for the childrens of v. So we will apply for child in v dot ref. Okay, if it is, then we will apply the function recursively build graph on that child. Okay, and after completing all the recursive process on child, we will append the value on topo. Okay, topo dot append v. Okay, and this is how we do. And after that, we will just call this function build graph on self. Okay, after this, before we start the backpropagation process, we will initialize self.grad as 1 for the loss function, and we will reverse the tuple list. Okay, I will explain why we do this. So let's say for v in reverse reverse topo list. Okay, topo, we will apply v dot gradient. Okay, function. Okay, so let me explain you how this works. Okay, now let's say if suppose output is a loss function and we want to apply back propagation, then what we'll do, we will do f dot backward. Okay, on this. So what will do is the self will get f as an argument over here. Then what we'll do, we will create, this will create two lists, topo as an empty list and visited. Okay, initially. Then this f will pass to build graph. Okay, we will check if the visited has f in it or not. So we know f is not there, so we will add f here. After this, we will find for check for the childrens of f. So we know the childrens of f's are c and e. So if the variable has childrens, then what we'll do, we will recursively apply the function again on the childrens. So we will apply the build graph on c, and we will see if the c is present in visited list or not. So it's not there, then we will apply c. Okay, and c, and we will check for the childs of c. So similarly, this will process go, and again we will find out a and b are the c final c, and we will check for the visited, and we will update the visited sets. Okay, after completing this, we will see that the a and b doesn't have any childrens. Then we will finally add these variables inside topo list. Okay, so we will add a and b, and after completing a and b, this will, the control will come over here, and we will add c, and this will move here, and we'll check for e. So e doesn't have any children, so we will directly set these values inside topo e and finally f. Okay, so if you see, the values are in in reverse order. So in order to apply backward from here onwards, so we have to reverse this. So that's why we used reverse function over here. Okay, okay, so now we have implemented this logic, so let's test it out. Okay, so I rerun all the cells and check how this is performing. Okay, so if you now can see that all the gradients are 0. So if I just do f dot backward, then all the variables will get updated. Okay, if I refresh this, then you can see this is working perfectly fine. Okay, let's implement a small realistic example, like implementing a neuron over here. So I will copy a small code snippet over here. Okay, so this is an example that we are going to use to test out our engine. Okay, so I have used data in such a way how the computation happens in the neuron, the same way we created our data. Okay, so before that we have to implement an activation function. We haven't yet, so let's do this. Okay, so we know already how the ReLU activation function works. So let's create a function for that. So ReLU, this will take self as argument, and what we'll do, we create another like example. What we'll do, we will create a variable to store the data of self instance. Okay, self.data. We know that if the values are positive, then we will pass it as it is, and if the values are negative, then we'll pass as 0. Okay, so output will be value max of 0 comma x 0 comma x. Okay, so whatever will be max, this will be passed as an answer forward. Okay, so this this will have children as self only, and the operator will be ReLU. Okay, so now we will implement the logic for backward propagation, that backward how gradients are calculated for ReLU case. So let's implement that. So we will create a function gradient for. Okay, what is the gradient of ReLU function? So let's see that. If the value is positive, okay, so then the gradient will be 1. If it is negative, then it will be 0. Okay, So let's implement this logic over here. Okay, so gradient will be we will apply if statement over here. So 0 if out dot data is less than 0, else 1. Okay, and multiply with out dot grad. Okay, similarly we will do out dot gradient is equals to gradient and return out. Okay, so now let's test this out on the dataset. Okay, I implemented the ReLU function. Okay, so if I run all the cells, let's see the output. Okay, so initially all those 0, and I have run the o.backward function, and let's refresh it, and we got the output. Okay, so all the weights, all the gradients are properly updated. Great. So yeah, this is how we build up the engine of Micrograd. Next, we will create the neurons and layers using this engine. Before we move on and start implementing the neurons and layers using this engine, let me walk you through what are the changes that I have made inside the engine. Okay, so to handle the issues of type errors and with the float and value object, we have created some more functions like reverse multiplication, true division, negative subtraction. This will handle the type errors that are happening during the calculations. Okay, and added one more activation function, tanh over here. So the formula of tanh activation function is tanh is e to the power 2x minus 1 upon e to the power 2x plus 1. Okay, and derivative of this function will be derivative is 1 minus 10 square x. Okay, as the same logic is implemented using code itself. Okay, over here if you see, right, to handle this exponential function, we have to create another function for that as well. So let's see. So yeah, if you see over here, this is the exponential function, and I use this math module to implement exponential function over here. The gradient of this exponential function is the function itself. Okay, if you remember, and we have also implemented the power function. Okay, this will be used during the loss calculation during the process of backpropagation. Okay, let's see. We are going to use new formula for loss function. Here we are going to use squared error. Okay, so in that squared error we are going to use the power function. That's why I implemented the function for power as well. So suppose if we have functions like x to the power n, then the derivative of this kind of functions is n into x n minus 1. Okay, the same I have implemented over here. If you see, yeah, this one, other into self dot data power of other minus 1. Okay, so we are all set to start the neuron implementation. So first we'll create a class neuron. Okay, and we create a init function, and this will take one argument as input. Okay, we will define a number of inputs that we want inside the neuron. Okay, and accordingly we will initialize the weights. Let's see, and we will create a list over here, and that value, whatever the value generated using the random module will be of type value. So for that we will use random dot uniform. This will generate random values between -1 and 1. Okay, and we will generate until number of inputs that we have passed on. Okay, so we will create a for loop for that for I in range number of inputs. Okay, so this will generate the weights for each and every input that we are feeding in. Okay, for each neuron we will create a bias. Okay, we will generate bias as well. This will be same random dot uniform -1 to 1. Okay, after that we will create a call function for this class. Okay, so this will take one argument x as input, and what we will do the summation. You remember Suppose if we have x1 and x2 as input, then we will generate corresponding weights w1, w2, and we'll do the summation of this expression. So this will be w1 x1 plus w2 x2, and after this we will add a bias. Okay, so same logic will be implemented here using code. Okay, let me clear this out. Let's name this variable as out, and this will do summation, and we will do wi into xi, wi for wi xi in for wi in a zip. We will create two iterators. One will be self.w, because these are lists, so we will pass it as an iterator, and we will create a pair of weights and corresponding inputs for summation. Okay, next one be x. Okay, and we will lastly add bias into it, and we will return the output. So out, and we will pass this output through 10h activation function for non-linearity, and we will also track the parameters that are generated during this process. So for that we will create a function parameter, and this will take self, and we will return the list of the parameters that are generated. So we will add bias into the list of weights. Okay, self dot w. Okay, so this is how we'll keep on track on the number of parameters that are generating. So let's check whether it is working as expected. So let's create a dummy data point. Let's say x is equals to 2.0 and 3.0. Okay, and we will create a model. Let's say model, this will be neuron, and we know that there are two inputs in x, so we'll initialize weights for that, and let's see the output. Okay, so model dot x. Okay, so yeah, this is the output that we got. Okay, right, so this is doing the calculations of this line and giving us the output, final output. Okay, so now we have created the neuron. Let's form a layer using these neurons. Okay, so for that we will create another class name as layer. Okay, so this will take two inputs, self, number of inputs, and number of outputs. So the number of neurons that are generated will be depend upon the number of outputs of the layers. Okay, so we will create self.neurons, and we'll create a list, and this list will contain the calculations of neurons that we pass on. So this will be number of inputs. Okay, so this will create a number of biases according to the number of inputs. Okay, so we're indirectly calling the neuron class over here. Okay, and the number of neurons will depend upon the for I in range number of outputs. Okay, number of output. So we have generated neurons for the layers. So let's create a call function for that, self and x. Okay, we will create a new variable output. Okay, that will store the calculation that happened in the neurons. Okay, so nx for n in self dot neurons, right, and we will return the output. Before returning the output, we will check if the output list contain only one value. So if that is, so we will only pass on the first value. If len of output is equals to 1, otherwise we will return the list of outputs itself. Okay, here we also do the track of parameters that are generated. For that we'll create function parameters. So we'll return a list p for parameters for neuron in self.neurons. Okay, and for p in neuron dot parameters. Okay, so let's see what is happening over here. So suppose if I say I want in 3 neurons inside one layer. It will check whatever the first it will check the list and list of self.neurons and check how many layers, how many neurons are created. And after that, after checking every neuron, it will initialize the parameters that are created inside the neuron using this function self neuron.parameter. Then we add this parameters that are generated inside a neuron into the list of layers. Okay, and that's how we will keep track on the parameters generated throughout the neurons and as well as in layers. Let's check how it's working. Okay, so let's create one layer. Let's name it as layer, and let's create layer of 3 neurons, so 2 by 3. Let's check. Okay, so this is creating 3 layers, and the outputs are here. Output of the neurons that we are getting over here. These are the outputs. Okay, so now we have understood how to create layers. Let's combine neurons as well as layers to form a complex neural network. Let's create another function for that. Let's name it as MLP. So if you remember, the network contains only one layer, then it is known as perceptron. Okay, and if it contains multiple layers, it is known as multi-layer perceptron. Okay, so for that we will create another init function. We'll take 2 inputs over here as well, but here in this case the number of outputs will be a list. Okay, number of outputs will be a list, number of input and number of outputs. And what we'll do first, we will calculate the size of the layers that we form inside the neural network. So for that we will combine both input and the number of outputs inside a list, single list, number of input and number of outputs. Okay, and then we will form our layers. Okay, so self.layers is equals to, it will be list, and layer will pass on 2 variables over here. First argument inside the size list, and the second argument will be i+1. Okay, and this is how we do, and this will be happen for I in range of length. This will depend upon the length of the list of outputs. Okay, so that's how we do len over here. So this will generate the number of layers that we mentioned inside the MLP. Okay, let's create a call function over here. This will again take one argument, x self and x, and what we'll do, we will iterate using for loop. So for layer in self.layers. Okay, we will do the calculations. So x will be variable in which we store the values, layer, and we pass on the value, and this way we will return the final output of whatever the calculation that happened during the for loop. And let's keep track the parameters here as well using the parameter function. Def is equals to parameters, and this will take self, and here the same logic we use, p for layer in self.layers, for p in layer dot parameters. So this is it. Let's check. Let's form a neural network, MLP. Let's visualize how the neural network would look. Okay, so let's do one thing. Let's create 2 neurons in input layer, 4 neurons in first hidden layer, 4 neurons in second hidden layer, and 1 neuron in output layer. So this is how it's gonna look. Okay, so these all are connected. So this will be, input will be 2, and we will pass on a list of n outputs. So first will hidden layer contain 4 neurons, second hidden layer will contain 4 neurons, and the output layer contain 1 neuron. Okay, so let's see. Okay, so this is how we are gonna get the output in after a single forward pass inside a neural network. Okay, now we will test this code that whatever we have implemented using a dummy data set over here. So if you see, these are the data points and these are the corresponding outputs of these data points. Okay, So what we'll do, we will implement a training process using a loop. So for now, let's create a loop for iterations. Okay, let's for k in range, let's do 20 for now, and we will do the prediction. So we will track the predictions inside a list by threads. So it will do model x for x in axis. Okay, and we will implement a loss function. So loss will be squared error. For that, sum and y spread minus y true and the power function into square for y true y spread in a zip iterator y s and y spreads. After getting the loss, we will apply the backward propagation process using backward function. So before that, we will initialize all the gradients of the parameters of the network as 0 using a loop. So for p in model.parameters, and we will initialize all of them as 0. So p.grad is equals to 0. Okay, and after initializing all of them as 0, we will apply the backward process. So loss.backward function. Okay, after that we will update the values. So for that, we will again create a loop. We to access the parameters, and let's say p.data is plus equals and minus 0.01, let's say 01 into p.grad. Okay, so what happening is here, let's see in detail. So suppose why I mentioned minus over here. So suppose at first iteration the loss was -4. Okay, so in order to make -4 comes close to 0, we have to add gradient on the data, right? So for that, we have added minus over here. So let's say suppose in second iteration it was 5, then what we'll do, we will minus gradient from data. So this will be handled using this minus sign. So suppose if the loss is minus, then the gradient would also be minus. So minus and minus will become plus, and that's how we will add gradient into data. Or in case of the plus loss, then the gradient will also be positive, and this way we will able to minus the gradient from data. Okay, that's why we added minus over here. Now we updated the data, and so let's check through printing these values. Okay, so for every iteration we will check how the loss is dropping using loss.data. Okay, and let's execute this. Okay, so if you see, the loss is reducing for every iteration. If I do it this multiple times, then you can see the loss is getting lower and lower for every iteration. Let's change this value to 0.1, so to see the faster conversion. Yeah, okay, so if you can see, now we are reaching 0.4. Let's check how the vibrate is looking. Okay, vibrates and y true. Okay, let's compare how this is looking. So we know ys actual, so it is getting closer and closer to 1. If you see, if I do it multiple times, then we will gradually gonna increase. And let's see, yeah, now you can see that the predictions are getting better and better at every iterations, and this is how the learning happening inside the neural network. Let's visualize how our network is now looking. So using the software dot loss. Okay, so if you see, then it is a gigantic network. It is very difficult to understand what is going on. See, this is amazing, right? So this is how the calculations happens inside the neural networks and how the network is built up. So this is a small visualization of that. Okay, see, yeah, Okay, so this is it in this video, and let me know your views inside the comment below, and thanks for watching.